So, we will quickly complete the proposition that was left over from the last class. So, this is the proposition that we looked at the end of the last class. So, if A contained in B are integral domains and A is integrally closed, suppose we have an element x in B which is integral over an ideal I, then x as an element in the fraction field of B is algebraic over K. What is meant by algebraic over K? It satisfies a polynomial. When you are over fields, if it satisfies a polynomial, it will satisfy a monic polynomial, because you can divide by the leading coefficient and say make the polynomial monic, but that is not the case when you are over rings. Okay. So, integral and algebraic have two different meaning in over rings, but in over fields they are all same. Anyway, let us just assume that it satisfies a polynomial. Okay. So, it is algebraic over K. This statement is fairly straightforward because it is integral over an ideal. So, it has a monic polynomial with coefficients coming from I, which is already there in K. So, it is certainly algebraic over K, but the second statement is more important, that if I take the minimal polynomial over K, then all these coefficients are coming from the radical of I. Okay. So, the first statement is fairly straightforward because it is integral, it is algebraic. Now, I take the minimal polynomial. So, I have x in some extension in some field. See, as a fraction field of B, fraction field of B will contain fraction field of A. So, as an element in fraction field of B, I can think of element x in fraction field of B over K. This element is algebraic over K, that is the first statement. Therefore, there exists a polynomial. Okay. So, I take the polynomial to be this f x minimal polynomial. Okay. What is minimal polynomial? So, if I have an element x which is in frac B and this contains K. Okay. So, let me call this K prime. Now, if I look at this Kx, okay, and I have the surjective ring homomorphism, the variable x going to the element x, p of capital X going to p of small x. This is a ring homomorphism, this is a field, this is surjective, therefore, the kernel is generated by an irreducible non-zero irreducible polynomial. There exists something in the kernel because x is algebraic, right. X is algebraic, therefore, there exists some polynomial which goes to 0. So, therefore, kernel is non-zero and it contains a polynomial. So, therefore, this has to be generated by a non-zero irreducible polynomial because this is a field. So, therefore, this is the kernel is generated by kernel phi is generated by some polynomial f x, which is because this is a PID. Kernel has to be a maximal ideal, therefore, it is generated by a non-zero irreducible polynomial, and hence this is irreducible, and that polynomial, the monic polynomial which is irreducible, which generates kernel phi, is called the minimal polynomial. That is unique, the monic polynomial which that is uniquely determined by this process. So, I take the minimal polynomial. Now, let us look at all the roots of this. In some, it need not necessarily be in K itself, not necessarily in fraction field of B k prime itself, it will be in some field somewhere. For example, if you take the polynomial x cube minus 2, okay, and B to be q cube root of 2, then all the roots of this is not here, right, it will be somewhere. Okay. So, just look at those all the roots, I mean look at a field where all the roots, or you just attach those elements to the base field k, look at that field, then you can write this fx as product of x minus xi. Now, another thing that one can notice is that, see, fx will divide, see, suppose x is integral over I, right. So, that will satisfy an integral equation that may be different from this fx, because this is fx is the minimal polynomial over q over k, but the other one is integral over I, that may be a bigger. So, what I mean, if I have an integral equation, see, if the integral equation is given by x power m plus b1 x power m minus 1 plus etc bm equal to 0, then this polynomial x power m plus b1 x power m minus 1 plus etc bm, this polynomial will be there in this kernel. Therefore, fx will divide this polynomial, which means all these roots xi's, they are all integral over I, because this is an integral equation with coefficients coming from I. We have, this is bi in I, we have taken the integral equation of x. So, this means all the xi's will be integral over I. Now, in the previous theorem we showed that the set of all integral elements will form an ideal in the integral closure. So, if I take, so what we are saying is that xi's are all integral over I, therefore, all the polynomials in xi's will also be integral over I. Now, look at what are the coefficients of this. They are all symmetric polynomials on x1 up to xn, right. A1 is x1 plus x2 up to xn, A2 is x1 x2 x1 x3 summation over all those. So, therefore, all the ai's are integral over I, all the ai's are integral over I, all the xi's are integral over I. Okay. Now, what did we prove in our earlier theorem? If I have an extension A contained in B, okay, if I take x plus x comma y in B, which are integral over I, then x plus y x y, the all integral elements here over an ideal I form an ideal. Yeah. We precisely described what the ideal is also. Radical of extension of this in the integral closure. Okay. So, these, the set of all elements here which are integral over an ideal forms an ideal in forms an ideal in between somewhere. So, therefore, if two of them are integral over I, their sum is integral over I, their product is integral over I, and so on. So, therefore, all the polynomials in x1 up to xn form they are all integral over I. In particular, all these coefficients a1 up to an, they are all integral over I, because a1 is summation of xi's, a2 is summation over ij xi xj. What is, see, this is the minimal polynomial. Minimal polynomial is this. So, if you just equate the corresponding degrees, ai's are all polynomials in xi's. So, therefore, ai's are all integral over I. Now, where are these ai's? This is the minimal polynomial of x over k. That means all of them are in the fraction field of A. A is integrally closed and we are saying ai's are all integral over I, in particular they are integral over A. Therefore, all of them have to be in A. But then see, if I look at all the coefficients, they are all integral over A, integral over I, then again applying the previous theorem that, so I have a ring extension like this, okay, and x in B integral over A implies that x belongs to radical of I extension. What is I extension? I C, where C is the integral closure of A in B. Now apply that in the case of A to K. ai's here are all integral over I, therefore ai belong to radical of I C, where C is the integral closure of A in K, which is A itself. So therefore all the ai's are in radical of I. Okay. This requires a little bit of field theory as well, but these are something that that we can one can explain as one goes through. So that completes the proof of going down theorem. This was what was remaining. Okay. So it would be a nice exercise to go through the proof again, try to write it down with all details. Okay. So now let us study what is called chain conditions. So let sigma be a partially ordered set with partially ordered set by a relation, I will denote this by less than or equal to, that is, what is a partially ordered set? I have the relation that is this is reflexive and transitive. And y less than equal to x and x less than equal to y implies x equal to y, and is such that then okay. So first let us see a nice characterization of what is meant by a chain condition. Okay. So the following are equivalent. Every chain A1 less than equal to A2 in sigma terminates, that is, there exists n naught such that ai equal to or an equal to an plus 1 for all n bigger than equal to n naught. that is a n naught equal to a n naught plus 1 equal to n naught plus 2 and so on. This is equivalent to saying that every non-empty collection non-empty subset of sigma has a maximal element. So, this is fairly straightforward, but let us look at the proof. Let us assume that every chain in sigma terminates, and let us try to prove non-empty subset has a maximal element. So, let us take S to be a non-empty subset of sigma. Okay. I want to say that this has a maximal element. Okay. What is meant by it does not have a maximal element? I take every element, there will exist something bigger than that. See, if S is finite, then we are through. Okay. If S is not finite, then I start with an element A1 in S. So, yeah, suppose sigma suppose S does not have a maximal element, then what do we have? Let A1 be in S, this implies there exists A2 in S. A1 in S cannot be a maximal element. How can it not be a maximal element? There exists something bigger than that. There exists A2 in S such that A1 is less than equal to A2, and then I keep saying this, A2 is not a maximal element, therefore, there exists something bigger than that, and keep going. Okay. So, we get an infinite chain which does not terminate, which contradicts our hypothesis 1. Okay. So, therefore, S has a maximal element. Conversely, to prove 2 implies 1, what do I do?
Form the subset by A1, A2 collection of
Exactly. So, here I want to say that my assumption is that every non-empty subset of sigma has a maximal element, and I want to say that this chain terminates. So, take S to be the collection of all these elements. Then S has a so I should say every non-empty subset of sigma has a maximal element in it. Or every non-empty subset contains a maximal element. So, then S has a maximal element, and that gives me, so call it A n, but A n is less than equal to, so A n say A n naught. Okay. Now, by this what is given to us is that A I is less than equal to A I plus 1. So, therefore, A n naught is less than equal to n naught plus 1, but a n naught plus a n naught is a maximal element, therefore, a n naught is equal to n naught plus 1 and so on. Since a n naught is less than or equal to a n naught plus k for all k bigger than 1 and a n naught is a maximal element, a n naught is equal to a n naught plus k, and that is exactly what the statement 2 statement 1 says. So, let us now let us look at some examples of such partially ordered set. If I take a module, so let A be a ring and M be an A module, take sigma to be a set of all submodules of this is a partially ordered set, right. It has partially ordered set with by what relation? The inclusion. So, there are two ways you can say. One is then sigma is a partially ordered set by the relation inclusion. Now, there are two ways you can say that. One is that if M1 M2 are in sigma, then M1 is less than or equal to M2 if and only if M1 is contained in M2. This is one way of saying. Another way is then M1 is less than or equal to M2 if and only if M1 contains M2. M1 is less than or equal to M2 if M1 is a subset of M2. That is one way. Another is M1 is less than or equal to M2 if M1 is a superset of M2 or M2 is a subset of M1. Okay. Both of them give a partial order structure to sigma. Okay. Now, we say that M is said to satisfy ascending chain condition if sigma satisfies 1 equivalently 2 in the previous proposition. That is, every increasing chain in sigma terminates, or every non-empty subset of sigma has a maximal element in it. Okay. And so here So here one we have to, okay, there is one more sigma with the relation subset. Okay, this is one. Two is M is said to satisfy descending chain condition if sigma ordered by the relation by this I mean M1 is less than equal to M2 if M1 contains M2, the second one which we described here. Okay. Satisfies one equivalently to in the previous proposition. Now let us look at some examples of these posets, partially ordered sets which satisfy ascending chain condition, descending chain condition, and so let me just make this definition once again. If an A module M satisfies ascending chain condition, then M is said to be Noetherian okay, and if M satisfies descending chain condition, then M is said to be Artinian. Noetherian module. Yeah. A ring is Noetherian if it is a module over Noetherian module over itself. Okay. We will see equivalent conditions and so on. So let us look at some examples of Noetherian, Artinian, and so on. What can you say about finite abelian groups? They are all Z modules, right? As Z modules, can you say whether they are they satisfy ascending chain condition, descending chain condition, and so on? There are only finitely many elements there. So if you take any ascending chain, it has to terminate, there is no way. Okay. And similarly, if you take any descending chain, it has to terminate, okay, because there are only finitely many elements in that. So therefore, R Noetherian and Artinian. Now what about Z? Does it satisfy ascending chain condition? So let us start with let us say 36Z. Okay. Can you tell me ideals that are that contain, see we are looking at an ascending chain. So what would be, can you think of some 18Z, 6Z, 3z. However, we take the factorization, if you take a chain like this, it will terminate, right. So, a more general justification is, if I have p 1 power alpha 1 up to p n power alpha n, if your ideal any integer, I mean this is a PID, therefore, every ideal is generated by some kz, every ideal is kz. Now, if I take k to be the prime factorization to be this, maximum number of elements in the ascending chain can be alpha 1 plus etcetera alpha n, right. If you take any ascending chain, it will have the there are finitely many ideals containing this one.
What we are taking sigma here?
Sigma is set of all submodules of what are the submodules of Z? They are ideals nz, right, subgroups of Z or ideals of Z, they are all of the form kz. So, if I take an ideal I, there are only finitely many ideals containing this ideal. Therefore, if you take any ascending chain, you start from here, you go ahead, there are only finitely many that contain this one. So, you cannot have an infinite chain. So, therefore, this satisfies. So, this is Noetherian. Everything is okay. For finite abelian group is an Z module. My sigma, whenever I consider module, my sigma is set of all submodules of the module under consideration. I fix a module and then I look at sigma, that sigma is collection of all submodules of M. Okay. So, Z is Noetherian. I mean, does Z satisfy descending chain condition?
2 power 4, 2 power 3.
You can right, you can have 2z, 4z, 8z. This is a strictly descending chain that never terminates. So, therefore, Z is not Artinian. So, we have now seen an idea, a module which is both Noetherian and Artinian. This is Noetherian but not Artinian. Now, let us look at an example where this is Artinian but not Noetherian. Okay. So, let us consider the subgroup G be the subgroup of Q mod Z. Okay, I am looking at the subgroup of Q mod Z which containing the all elements of order p power n for a fixed prime p and some n. Okay. That means when is it and what are the elements of G? I should have some say A by B bar such that p power n times A by B is an integer, or in other words p power n times when is, see what is the order here? Here this is additive subgroup, right. We are looking at the additive subgroup of Q mod Z. So, what is meant by an element having finite order, a p power n order? You sum this up p power n times, it should be 0, but what is 0 here? Integer, or in other words it should be p power n, I mean b should divide p power n, right. So, therefore, what we are looking at is okay, and a is any integer. Now, we want to check whether this is this satisfy ascending descending chain conditions and so on. If I look at the element 1 by p power n, okay, this is, what can you say about the I mean the bar of the equivalence class of, I will remove the bar when I write 1 by p power n, I mean the corresponding equivalence class here. What is the submodule generated by this? I fix this n, okay, fix n and G n be the submodule or subgroup generated by 1 by p power n. And what would this be? One by p power n, 2 by p power n, 3 by p power n, and so on, right, and p power n minus 1 divided by p power n, right. What would be minus 1 by p power n? Will this be an element here? What would this be? This is what? By p power n. So, similarly minus 2, minus 3, so they are all here. So, therefore, this is a group of order p power n, right. Now, G n is, what can you say about G n and G n plus 1? Can you say something about these two subgroups? Of course, order of G n plus 1, can you have some comparison? Order of G, see this is for any n, order of G n is p power n. G n is contained in G n plus 1, right. And if you take any element in G, it will be in one of those GIs, right. Moreover, suppose I take any subgroup H of G, I take a subgroup H of G, H be a subgroup of G. Okay, so let's look at finite subgroup. Finite. If it's a finite subgroup, I would say, I am saying that H has to be, okay, so this means, see every element of H, every element of G will be in one of those GNs. So that means H intersected with Gn, this is non-empty, right, for some n, okay, this is non-empty for some n. So, let A by p power n be in H be the element of largest order, be an element, there could be many. See, for example, in this one, this is not the only generator of Gn, right. If I take any element which is co-prime with P, right, if A is co-prime with P, A by p power n will generate Gn again. So, we do not really have to look at elements which are only one. So, there would be many generators. Similarly, there could be many elements of largest order. So, I look at be an element of largest order in H, okay, and so I claim that I will assume A p, because we are anyway talking about rationals. If A by p power n, if A has a factor of p, I can always cancel this. Then I claim that H is Gn. I mean, that is kind of clear from what we have. Okay. So, I will leave this as an exercise. Okay. So, what we have shown here is that every finite subgroup is Gn. Suppose H is an infinite subgroup. What does that mean? It will contain A by p power n for every n where A and p are co-prime, but then that will imply that it will contain all the Gn's, and that would imply that it is equal to G. So, therefore, if and this is infinite, then H is equal to G. So, what we have shown here is that the only subgroups of G are of the form Gn. Now, this is an ascending chain, right. So, that will never terminate. Right. This is G1 contained in G2, contained in G3 and so on. That is an ascending chain that never terminates. Therefore, our G does not satisfy the ascending chain condition, it is not a Noetherian module. But now, what about the descending chain condition? I start with a submodule of G. How does any submodule of G look like? Gn for some n. Now, you start with Gn, there are only finitely many Gm's contained in Gn. So, therefore, it satisfies Artinian property or descending chain condition. So, this implies, therefore, G satisfies descending chain condition and does not satisfy ascending chain condition. So, therefore, G is an Artinian Z module but not a Noetherian Z module. Now, if I take Kx, what are the Kx submodule? So, this equal to A equal to M. What are A submodules of Kx? Ideals, right. So, if I take sigma, sigma is collection of all ideals. Now, how does, can we say something about ascending chain condition, descending chain condition and so on? Exactly like Z, right. If I take any ideal here is a principal ideal and this is a unique factorization domain. So, therefore, I have a every ideal is some so there are given any element it has only finitely many factors. So, therefore, given any ideal there are only finitely many ideals containing the given ideal, therefore, ascending chain condition is always true, but descending chain condition is not true because you can start with f x containing f x square containing f x cube and so on. So, therefore, this is Noetherian but not Artinian. So, we have seen examples where it is both Noetherian and Artinian. They are either Noetherian but not Artinian, or it is Artinian but not Noetherian. Now, if I have this example, fix a prime p G b equal to a by p power n a in z p prime n bigger than or equal to 0. That means, I am taking all the no, not fixed prime p, see I am writing p a prime here, which means p is varying. I am looking at all the primes. I am not looking at elements of the form, say for example 1 by 6, okay, only some integer divided by power of prime. Okay. Now, G cannot satisfy. So, this is, let me write this as an exercise. G does not have an descending chain condition. As a Z module, G does not have ACC as well as DCC. Okay. We will prove more about Noetherian and Artinian modules later.